Welcome back to Discrete Math. In this lecture, I'm going to talk about structures and interpretations, discrete structures, and what we intend their elements to mean. And the whole idea here is that when we establish a correspondence between symbolic terms in discrete structures and objects in some real or imaginary world, we can then reason about that world by manipulating those symbols. So we'll make that idea precise in the next half hour or so. So a review of the concept of discrete structures as I've characterized them in this class so far. For our purposes, a discrete structure comprises four key elements: a type that defines a set of objects, which we can also call elements of the type or values of that type, operations on values of that type, properties of objects of that type, and relations involving objects of a given type. So for an example, think about character strings. In fact, think about the set of all possible character strings. You've got the empty string, you've got the string with just the letter A, the string with just the letter B, the string with just the letter C. For each element of your alphabet, you have a single character string. And then to the A string, you can append an A to get AA, you could append a B to get AB. Eventually, you get through AZ, then maybe you go to BA, BB, BC. And you can see that you can construct an infinite set of strings in this way. Okay, now we're going to need to have a way to characterize finitely in a few words, but precisely, all and only the elements of any such set. And so one way to do that, almost precisely for strings, is to say that a string is either empty, in which case there's no characters at all, or it's a character selected from whatever alphabet or keyboard you're using, okay, followed by a smaller string. Okay, now wrap your head around that. A string is either empty or it's a character followed by a smaller string. So the empty string is the empty string. The string A, think of it now as the character A followed by the empty string. And that itself is a string. A followed by the empty string is one bigger string. Now think about the string AB. Well, that's A followed by the string B empty string. Okay, now think about the string ABC. That's the string A, followed by the string BC, empty string. Of course, BC empty string is the string, well, you get the idea, okay? So a larger string can always be formed by taking a character and putting it at the beginning of a one smaller string. And in that way, by adding different characters at the front of any given string, you can always build a one bigger string than the one that you started with. And of course, the smallest string that you can start with is the empty string. And so from there, you can get the set of all possible strings of characters selected from, again, some alphabet that needs to be specified here. I've just used the 26 letters of the English alphabet as an alphabet, but you could take the alphabet of your keyboard or the alphabet of ones and zeros or what have you. Okay, so that's an example of a type. Now, what about operations on strings? Well, I mean, one obvious operation on strings is to essentially add two strings together. We usually call that operation append. So if I have the string AB, and I won't say empty string at the end anymore, okay? If I have the string AB and the string CD, if I say AB plus plus CD, meaning append AB and CD, then I get back the string ABCD. Okay, now we can talk about properties of strings. So here's a property that you might never really have thought about before, but you could say a property is the property of being of length 3. Okay, now some strings have that property, like ABC. Some strings don't have that property, like the empty string, which is of length 0, or the string AB, which is of length 2, or ABCD, which is of length 4. But the string ABC, BCA, CBA, XYZ, PQW, and so on and so forth, all do have that property. Okay, the property of having length 3. So what's really interesting about properties is that they specify sets. The property being of length 3 is tantamount to the definition of the set of all strings of length 3. Right? Every string in the set of strings of length 3 has the property of being length 3. And any string that doesn't have that property, well, doesn't have that property, it's not in the set. So sets and properties turn out to be intimately related. And in fact, in set theory, we really characterize the elements of a set by stating what property the elements of that set have, that distinguish elements of that set from any other set. Okay, so finally, let's talk about relations. Let's talk about relations. Okay, so equality of strings is a relation. So you could say that ABC and ABC have the equality or are in the equality relation, but ABC and DEF are not. So the pair of strings ABC, ABC has the property that the two strings in that pair are equal, but the pair of strings ABC, DEF don't have the property of being equal. So that pair, we would say ABC, DEF, is not in the equality relation. Okay, so now you can think about the equality relation as a set of pairs. The set of all pairs, and only those pairs, whose two component parts are the same string. So is XYZ related to XYZ by equality? Yes, indeed. Is the string ABC related to the string CBA in the equality or by the equality relation? No, it's not. Okay, so now close your eyes and imagine the set of all pairs of strings where the two elements of each pair are the same string. That set of pairs, think of it now, and mathematicians think this way, they think of that set of pairs as a relation. A binary relation because each tuple has two elements. Okay, and we can talk about ternary relations where instead of pairs we talk about triples of objects, or quaternary relations where we talk about 4 tuples or 5 tuples or n tuples where n is some arbitrarily large number. Okay, so we think of a relation as a set of tuples, pairs for example is the simplest example, where all and only the tuples in some relation have some particular property. They bear some particular relationship to each other. Another example of a relation on strings is what computer scientists would call lexicographic ordering, where we say that, it's not just computer scientists, I mean elementary school kids learn about this. It's also known as alphabetic ordering. So we would say that ABC is less than CDE in an alphabetic ordering. It appears first, right? ABC comes before DEF or XYZ or PQR, okay? And so we would say the pair ABC, XYZ is in the lexicographic ordering relation, which we could use like a less than or equal sign to represent, okay? So we can say that ABC is less than XYZ, for example. Okay, but is the pair XYZ ABC in this relation? No, because XYZ doesn't come before ABC in lexicographic order. So whereas the pair ABC XYZ is in the less than relation on strings, the pair XYZ ABC is not in the lexicographic ordering or alphabetic ordering relation on strings. Okay, so to sum up this slide, we really want to think of a discrete structure as a type that characterizes a set of objects plus a set of operations that do things. You can think of them as functions that do things with objects of a given type, like adding two of them together. We think about properties of objects of a given type. So let's actually do a little bit more work on that. Imagine that the objects we're talking about are just natural numbers, okay? Ordinary mathematical numbers from 0, 1, 2, 3, all the way on up. Can you think of some more operations on values of that type? Addition, subtraction, multiplication, exponentiation, the predecessor function that takes a natural number and returns one less than that number. a successor function that takes a natural number and returns one more than that natural number? How about the factorial operation that takes a natural number and returns its factorial? Okay, or the squaring operation that takes a natural number and returns its square. These we think of as operations on values of a given type. We can think about properties of values of type natural, of values of properties of natural numbers. So natural numbers have properties of being even, being odd, being greater than 10, being equal to 7, being perfect squares, being I don't know. You can make up your own examples of properties of natural numbers, and we've already talked about the less than relation on strings. The less than relation on natural numbers is one example of a easy to understand relation on natural numbers. So now we introduce the really, really important concept of domains and interpretations as they relate to discrete structures. So here's how you can kind of think about this relationship between discrete structures and domains of discourse, as illustrated in the diagram on the slide. Discrete structures think of them as kind of symbolic things, right? The elements of a discrete structure, think of them as being symbols of some kind, and an interpretation explains what each such symbol means in some other domain of discourse. Okay, so here are some examples to try to make this concept of a symbolic set of discrete structures and an interpretation that tells you what each such discrete object is intended to mean in some domain. So we can use character strings, which are, as we've already discussed, discrete structures, right? A string is either empty or it's a character followed by a smaller string. But we can now use strings to represent people in the real world, okay, by name, right? And so we see here this fundamental concept of using symbols on one hand to represent things in the real world on the other hand. We can use sequences of digits, in other words, numerals, to represent numbers. Right? There's many different ways to represent the mathematical concept of threeness. It could be ///, that represents 3. It could be the typical, way in which we write the numeral 3. It could be 1, 1 if we're representing 3 in binary. Those are numerals, so there's many different symbols that can represent the same concept. The concept of threeness lives in the domain of mathematics. The concept of strings of numerals lives in a domain of discrete structures. We've already in this class used binary trees of strings to represent ancestry relationships between human beings. We've used Unary trees to see how we can represent the organization of files in a file system on your computer. And we'll see as this class goes along that we can use trees of terms to represent expressions in mathematical and other formal languages, like different logical languages. We can even understand a computer program as a tree of commands. So you can think of, for example, an assignment command. Think about an if, then, else command. It's if, some Boolean expression, then one smaller command, or a different smaller command. So here we have another example where bigger commands are built up out of smaller commands, all the way down until you get to commands like assignments. X = 7, that's not built up out of smaller commands. How about a while command? Is that built up out of smaller commands? Sure. While, Boolean expression, some smaller command. While Boolean expression, smaller command, is itself a bigger command. Okay? And so trees of commands can be used to represent computer programs, and then our interpretation of those computer programs is that they mean some computation. And kind of the magic of computer science is that we can automate the evaluation of computer programs to determine what they mean, which is to say what they compute. Okay, so the takeaway message from this slide is that you really now need to begin to think in terms of symbolic domains and domains of discourse, where the symbols in the symbolic domain are interpreted as meaning something in a domain of discourse. And of course, domains of discourse can be widely varied, I mean, infinitely variable. So a domain of discourse can be mathematical, it can be imaginary, it can be social, it can be chemical, it can be fluid flows. I mean, in some sense, what we do in computer science is we go out and try to understand a domain and then to build symbolic representations of that domain that can be manipulated automatically in the memory of a computer. Then the computer manipulates those symbols, and we interpret the result of those manipulations as also corresponding to what's in the domain. Okay? Now, just as discrete structures we can think of as sets of objects and with operations and properties and relations, that's a natural way also to think about things in the world. So, think about a real-world physical domain of electric vehicles. Okay, just think about all the Teslas that are driving around. That's our domain of discourse for this little tiny mini conversation right here. Okay, those objects have properties: make, model, maximum velocity, current speed, fuel level, year of manufacture, and so on and so forth. Take a second and see if you can come up with at least 2 other properties of Teslas. Just think about it for a second, and it's pretty easy. Paint color. Weight, body material, whether or not they have leather seats. Yeah. So this notion of properties of an object, it's just a very, very, very natural way of thinking. We do it all the time without thinking about computer science or discrete math. We can also think about relations involving Tesla vehicles. So for example, you could say 2 Teslas are related if they have successive serial numbers. Okay, or when we talk about relations, we can also talk about relations involving different kinds of objects. So a relationship between, we could think about the relationship between Teslas and charging stations, where we say a Tesla T is related to a charging station S if and only S is the charging station that's closest to the Tesla T. Okay? So think you're driving down the road, your Tesla's running out of electric charge, and there's all kinds of charging stations out there, but you want the one that's nearest. Okay? You want to know the charging station that is related to your Tesla by this nearest relation. Okay, so it's very natural to think of objects in the real world as having properties, operations that apply to these objects, like charging, right? You could say charging a Tesla is an operation that changes it from one kind of state to another state, from discharged to charged. And relations. All these concepts that apply in the world of discrete structures are just naturally apply in the real world. And a key idea, of course, is that we use objects, operations, properties, and relations in discrete structures to model and represent and reason about objects, operations, properties, and relations in the real world. Right? Think about a social domain of discourse. Okay, the objects in this world are real, let's say, living human beings. Okay, properties of these objects include height, weight. You can name innumerable properties of people, whether somebody's nice, whether they're gregarious, whether they're, healthy or ill, whether they're under 10 or at least 10 years old, and relations. We often think in terms of binary relations between people. So, does person P1 have a crush on person P2? And does person P1 like P2? Does person P1 work for P2? Is person P1 the child of P2? Is person P1 the parent of P2? Is person P1 the grandparent of P2? innumerable relations between people. And these relations are not only binary. Think about married people and the person who married them, right? You could have a married by relation where P1, P2, P3 is in this relation if P1 and P2 were married by P3, and otherwise a triple of persons is not in this relation. Take a second and just think about that example. A person P1 is related to P2 and to P3 if P1 and P2 were married by P3. Okay? Not every set of three people belongs in that relation, right? Not every two people were married by some arbitrary third person. In fact, the relation is rather sparse. Good. Okay, so one of the things we actually talk about in this class is properties of relations. So when we get to considering mathematical domains as the domains of discourse that we then represent using discrete structures, things actually start to get quite interesting then, and that's where, we're headed in this class. So to make that idea more explicit, abstract world mathematical domains can be domains of discourse. Okay, so let's again think about natural numbers. Now, we've been thinking about natural numbers in our minds since we were probably before going to school, right? So people have an intuitive sense, these days anyway, of what it means to be 0, 1, 2, 3, 4. We use these sounds, a certain kind of symbol, to represent these abstract concepts, the concept of threeness or two-ness or fourness, of being 4, or of being 1, or of being 117. And we have clear ideas of what properties these math world objects have. So natural numbers, for example, can be equal to 5 or not equal to 5. That's a property of being equal to 5. A natural number can have the property of being prime. It can have the property of being even, or of being odd, or of being perfect, or of being a perfect square. Okay? And again, we can talk about relations in the world of real numbers, in the domain of natural numbers, in the real world domain of natural numbers. Now, it's a weird domain, right? Because it's not a physical domain, and it's certainly not just a made-up domain. But it's a domain that's abstract. It's in our minds. We hold arithmetic, concepts of arithmetic in our mind. Okay? But in order to reason mathematically, we need to represent those things in our mind using symbols. Okay, and so we use strings of digits, for example, numerals in other words, as representations of natural numbers. And then we can define operations on those representations that allow us to compute using symbols about that actual mathematical world. A lot of what you learned in first, second, third, fourth grade maybe in arithmetic was how to do operations on particular representations of natural numbers. So how do you add 2 3-digit natural numbers, for example? Well, you have to do this, and that maybe there's a carry, and you have to then add 3 things, and maybe there's another carry, and so on and so forth. That's an operation on representations of natural numbers. Okay, so if you add the representation 5 and the representation 6, you're supposed to get the representation 11, where 5 represents the number 5, the digit 6 represents the number 6, and the result of applying this addition operation on these two representations, the digit 5 and the digit 6, gives us a numeral 11, and that has the magic property of actually being the right numeral to represent the mathematical sum of the arguments to the operation. So again, I want you to start to think in terms of these relationships between domains and representations. And the idea then is we can compute and reason about domains by performing operations on symbols that represent things in those domains. Okay, and some of those symbols are definitions of functions that correspond to operations in a given domain. So in terms of arithmetic, for example, we have the mathematical concept of addition, and then we have algorithms, for example, for adding representations of natural numbers. In the memory of your computer, natural numbers are represented by strings of zeros and ones. They're represented in binary, and we have operations that are typically implemented by hardware circuits for doing addition of binary numerals. Okay, and those operations on binary numerals have the property that they compute the right resulting numeral to represent the sum of the numbers represented by two argument numerals. Okay, again, think about that correspondence between the symbolic domain of kind of discrete structures, or even of non-discrete structures. I mean, all of mathematics and physics work this way. Correspondence between the symbolic domain and the domain being represented. And by the way, a bullet that's not on this slide is we can use symbolic representations of imaginary worlds, like, in computer games or simulations of things that don't actually exist. Good. So this correspondence between a kind of symbolic world of, let's say, discrete structures and a quote unquote, I'll call it a real world, but it could be an imaginary world, it could be an abstract mathematical world, we'll call it a domain of discourse. Sometimes I'll use the term world for domain of discourse, and discrete structures or symbolic representations or machine representations to talk about the symbolic kinds of things on the left-hand side of the diagram here. Okay, so let's make a note about vocabulary. We use the word interpretation to define a relation that associates elements of a discrete structure with what these elements are intended to represent in a given domain. Okay, good. Now, we can often use one element of some discrete structure to represent lots of different things, right? We might use the binary digit 101, which we think of as representing decimal 5, as representing 5 apples, or 5 oranges, or 5 miles per hour, or 5 people, 5 employees, 5 animals, 5 atoms. So there's not a predetermined association between symbols and things in the world. We select symbol systems that are appropriate, or we design symbol systems that are appropriate for representing what we want to represent, what we want to compute about, and what we want to reason about in the world. Because we have to set up these correspondences, these interpretations between the symbolic stuff and the stuff in the domain that we want to represent. Okay, so as computer scientists, and as software designers, and as logicians and mathematicians, we design and then use discrete structures and other kinds of mathematical structures in general to represent and reason about logically and often mechanically, which is to say via automation, to represent and to compute and reason about real and imaginary domains. Okay, so a last little exercise before I go to the next slide. I'd like you to think about a program that you've written at some point in your life. Now think about the symbolic things in that program, like the variables and the values that they hold, and what those values actually look like a little bit in the memory of the computer. Now think about those things as symbols. Okay, what in your example were those symbols meant to represent in some other domain, in some application domain? Maybe you wrote a program in which variables represented images, for example, okay, or in which variables represented points in time, or where variables represented the velocities of some kind of vehicle, or where functions like accelerate in your program represented operations like really genuinely pushing down the gas pedal in the real world of some automobile, maybe an automobile that's being managed and manipulated by a computer program. Okay, so what kind of discrete structures did you use in your program to represent things in the world? what was the intended world or domain of discourse that you were representing, and give a few, in your own mind, come up with a few examples of elements of the discrete structures and what they represented in that world. Okay, and this is an exercise that's meant to help your brain solidify this notion of this concept of a relationship between a domain of discrete objects and a domain of real world things that those discrete objects correspond to and represent. So let's take a somewhat in-depth example in which we're going to represent the domain of the mathematical domain of the natural numbers on the right in this diagram with a particular kind of representation of the natural numbers that is, in essence, what we call a unary representation of natural numbers. You might be familiar with the concept of binary, in which we have two digits, 0 and 1, that we string together in order to represent numbers, but unary is even simpler. You learned it in probably first grade. For every number you want to count, you just make a mark. So to represent 0, no marks. To represent 2, 2 marks. To represent 5, 1, 2, 3, 4. And typically so that we can see better how many marks there are, we sort of group them in fives, but that's not really essential. Okay, the concept of a unary representation is there's just one mark for each increment or each successor of a natural number. And if we have a natural number written down as a sequence of slashes, we can always represent the successor or one more than that number by just adding one more slash at the beginning. Okay, so that actually gives us a sense of the structure of the natural numbers represented, at least in unary, where a natural number is either 0 or it's a slash in front of a smaller natural number, right? If we have any natural number written down, whether it's 0 or more than 0, we can represent the successor or one more than that number by just adding one more slash. Good. Okay, so on the left-hand side in this diagram, we have a specification, a kind of informal specification of a discrete structure that we'll call NAT. That's actually the name of a type with some associated operations, properties, and relations. The type we'll call NAT, and the details of what that type of object, the set of symbols that are the set of objects that are in that type, we'll talk about those in just a minute, although I've already given you a heads up on what it's going to look like. And then on the right, we have the domain of like the conceptual, mathematical, the real world of natural numbers. Okay, the natural numbers, mathematicians often represent the set of natural numbers using that blackboard font, capital N, that you see in parentheses at the top of the diagram. Natural numbers are so widely referred to and reasoned about that mathematicians use that symbol to represent the set of natural numbers. Okay, so going back to the left-hand side, we have the discrete structure that we'll call NAT, which comprises a type, which we'll call NAT, a set of operations like successor, given a NAT, give me one more than the NAT, addition, given me two of these numerals, if you want to think of them that way, compute the numeral that represents the sum of the numbers that the given numerals represent. Okay, let me say that again. So on the left, we have the symbol world. On the right, we have the domain world of natural numbers. In the symbol world, we use numerals to represent natural numbers. In unary, numerals are just sequences of marks. Okay, now given two sequences of marks, we want to compute a new sequence of marks such that the new sequence of marks represents the number that is the sum of the numbers represented by the two given sequences of marks. Okay. Stop the video here if you need to, rewind, put it on slow, and make sure you understand that concept, because it gets to this notion of this relationship between the symbol world and the world being represented, where once we've represented the real world in the symbol world, we can do manipulations in the symbol world that actually are guaranteed to make sense back in the world of that we're back in the domain world that we're modeling and computing about or reasoning about. Okay, so going to the bullets, the world in this case is the mathematical domain of the natural numbers. That domain includes 0, 1, 2, 3. It's all the non-negative integers, if you will. As computer scientists and as mathematicians and logicians, we need to represent these abstract concepts that we call natural numbers. And not only the numbers themselves, but operations on them, properties and relations among them. And a key idea is that many different representations can be used. As I said, we can represent natural numbers using unary representation, binary representation, octal representation, in which we use the digits 0 through 8 to represent natural numbers. Okay? So if we wanted to represent the natural number 7, it would be just 7, but if we want to represent the natural number 8, it would be 1, 0. Okay? 8 to the first power plus 0 times 8 to the 0th power. 1, 0 represents 8. 1, 1 represents 9. 1, 2 represents 10. Okay? Or we can use decimal numbers, or we can use hexadecimal numbers, okay, which are a base 16 notation for representing natural numbers. Okay, so the digits there are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. In this representation, the digits 0 through 9 represent the numbers 0 through 9, and A is 10, B is 11, C is 12, D is 13, E is 14, F is 15, and then 1, 0 would be 16, 1, 1 would be 17, 1, 2 would be 18, and so on and so forth. So in each of these representations, we use the position of a digit in a string of digits to represent the coefficient of the base raised to the power of that position. So digits in the 0th position all the way to the right represent, some number times the base to the 0 power, which is some number times 1, then some number times the base to the first power, then one number times the base to the second power, and so on and so forth. The main point is not to understand the details of hexadecimal notation at this point, but really to understand that there are many different ways to represent the natural numbers. We are going to focus on unary representation, where /// or SSS or ****, whatever symbols you want to use, represents the number 3, rather than binary, where we would represent 3 as 1, 1, or decimal, where we would represent 3 as the digit or numeral 3. Okay, so we're going to define and spend a lot of time learning how to define operations on unary representations of natural numbers using a type that we're going to call NAT. Okay. So now let's get down to business. What does this type look like? Well, let's look first at the table on this diagram. In the left-hand column, we have terms or symbolic objects. And on the right-hand side, we have the domain of the natural numbers. And here I'm just using decimal notation to represent the numbers 0, 1, 2, 3, and so on and so forth. So here's the idea. We're going to use the symbol 0 to represent the number, the natural number, in our mind, 0. And given any natural number, such as 0, we're going to use successor, S-U-C-C, the successor. We pronounce that as successor. We're going to use the symbol successor of 0 to represent 1. Okay, we're going to use the successor of 1, which is represented by successor of 0, to represent 2. So successor of 0 represents 2. The successor of the successor of the successor of 0 represents 3. And so you see we have a sort of natural unary notation to represent natural numbers, where we represent the number 0 not by a blank page, but by the symbol 0. And where, let's look now at the final row of this table. If we want to represent one more than some number n, we use successor of n for that purpose. Okay, so this is a little bit complicated. But suppose, well, let me ask you this. Let's make it concrete. Suppose I'm given a representation here, successor of successor of successor of 0 to represent 3. How would I represent 4? Yeah, just stick another successor in front of that. Okay, so that term, successor of successor of successor of successor of 0, is itself a term of type nat. Okay, so what we have in the left-hand column of this diagram are the first 1, 2, 3, 4 terms of type nat. So the values of this discrete type are these strings of symbols, including 0, successor of 0, successor of successor of 0, successor of successor of successor of 0. And you can just keep adding more and more successors at the front of such a string to represent a number one bigger than the number represented by the string that you just added a successor to. Okay? And so if we look at the last row in this chart, if n is any term of type nat, whether it represents a 0 number or some large non-zero number, for example, then successor of n represents one more than what n represents. Wrap your head around that. The term, the symbolic term, successor of n, represents, or we interpret as meaning, one more than the number represented by n. Successor of n represents one more than the number represented by n. N is a symbol. Successor of n is a symbol. If n represents some number 7, for example, then successor of n represents one more than 7, which is to say 8. So now look at the words to the right of the diagram. Think of each occurrence of SUCC as being like a slash on a piece of paper when you write this with paper and pencil. Okay, we tick off one slash for each thing being counted. Using one mark for each thing being counted is what we mean when we say that we're using unary notation. It doesn't matter if we use slashes or stars or exclamation points or dashes or periods or dots or Qs or strings of characters like SUCC. Just think of that as like a slash. Okay, this is really the simplest of all possible notations for representing numbers. It's probably what people, invented when they first started thinking abstractly. You'd make one mark for each person in your community, or one mark for each person that, Tommy Jones managed to capture to eat that night when doing hunting and foraging. Okay? It's a great notation for representing natural numbers. It's extremely simple to reason about, and a lot of automation of reasoning is very straightforward using unary notation. The one downside to using this notation, and you've always recognized this, is that you have to write really long strings to represent really large numbers. Like to represent the number 1,000,000 in binary, it's just 1, 0, 0, 0, 0, 0, 0. It's 7 digits. How many digits do you need to represent the number 1,000,000 in unary? Yeah, 1,000,000. Right? So it's not a very good notation for representing and computing with or reasoning about large numbers. Okay? But we'll find in this class that it's a fantastic notation for reasoning in very straightforward ways about natural numbers, their properties, for defining operations on these numbers, and so on and so forth. Okay? Good. So now we can go to the top of this slide and think just a little bit more abstractly about what we've said. We see that we want to define a set of symbols, a set of these, unary representations of natural numbers that are either 0 or successor of 0 or successor of successor of 0 or the successor of any one smaller natural number. And there's going to be an infinite set of those, right? If you want to represent the number 1 trillion, well, it's 1 trillion SUCCs followed by 0. Okay, and you can always represent a number one bigger than any number you're given by just adding another successor in the front. Okay, so how do we specify that infinite set of symbols, of symbolic strings, without writing them all out? And the answer is, again, we're going to use this notion of an inductive definition, which is a sort of a circular definition, but where the circularity doesn't keep going forever. Okay, so think about some natural number. It's one more than a number that's one smaller. My cat just stepped on my keyboard. And that one smaller number is successor followed by yet a smaller number. And because the number you started with was maybe very, very large but finite, it's represented by a finite sequence of successor constructors, if you will, applied to the zero constructor. I'm starting to use some new language here. And so you can always strip away a finite number of successors to get down to zero, okay? Because you can represent any natural number. It's got to be finite, because infinity is not a natural number. And so no matter how large it is, it's some finite number of successor applications applied to zero at the end of the day. Okay, and so how do we specify that set? Well, inductively. A value of type nat is either the term 0, and remember, we're defining again a set of symbolic representations. So 0 is one of these symbols, and given any symbol of type nat, 0 is of type nat, the successor of 0 is of type nat, the successor of 0 we want to be of type nat. So the way that we capture all the rest is we say, if you give me any n of type nat, if I attach a successor at the front of it to get the term successor of n, then that term is also in the set of values of type nat. And those are all of the values that there are in the set of values of type nat. Okay? Cat. Okay, good. And as we said before, we interpret successor of n as representing mathematically the successor or one more than what little n represents. And I'm sorry, I think I typed little n as a big N at the end of this bullet. Okay, so that is how we're going to build a discrete structure, or at least the type part of the discrete structure, the set of terms of this nat type. That's how we build that set of terms. Now we need to think, well, how would we then build a representation and implementation, if you will, of operations, okay, that are faithful to the actual corresponding operations in the domain? What does an operation of addition on objects of type nat have to look like if the result of adding two nats is going to correspond to the result of adding what those two nats actually represent in the domain of natural numbers? So let's think about it. Let's think about it concretely at first, and then we'll think about it a little bit more abstractly and kind of boil it down. So here, I've already said a natural number, a nat. Well, actually, no, let's talk about natural numbers. Not the type nat, but real natural numbers in the real mathematical world of arithmetic. How is that set defined? How do mathematicians think about the set of natural numbers? Well, it turns out that they think about them inductively in just the same way that we've explained here. So that gives rise to the famous set of axioms or rules for defining the natural numbers called Peano's axioms or Peano's principles. That's P-E-A-N-O. So I strongly recommend that you take a look at the Wikipedia page or other material out there on Mr. Peano, who basically provided the first, really solid set of principles that define all and only the set of natural numbers. So to put it very simply, a natural number is either 0 or it's the successor of a smaller natural number. And any natural number can be built in this way. You start with 0, and if you want to represent 7, you apply the successor function to that 0 7 times, and you get 1, 2, 3, 4, 5, 6, 7. Okay, now the add operation is defined mathematically as a function that takes two natural numbers, which you can now think of as being represented in this kind of unary notation, and that adds them together in a way that's defined by just two cases. And those cases correspond to the two ways in which you can build a value of type nat. Remember, a value of, well, the two ways in which a given natural number can be built. It's either 0 or it's the successor of some one smaller natural number. So let's suppose that we want to add n and m. And the rows of this table give some different examples. Suppose I want to, let's look at the first row. Suppose I want to add 0 and 3. That's pretty easy. The answer is 3. Now, what if that 3 were replaced by a 7? Well, 0 plus 7 is 7. Now let's generalize. Let's leave n to be 0, but instead of 3 or 7 or 59 or 1,000,006,000,006, let's just use a symbol here that stands for any natural number, m. Little italic m here. What's 0 plus m? It's just m. Okay, so there's rule number 1. It's a general purpose rule for doing addition. It's the easy rule, and it's the rule corresponding to the case where the first argument is 0, rather than being the successor of some one smaller number. There's only two cases. The first argument is 0, or the first argument is not 0 and is therefore the successor of some one smaller number. Okay, so let's take a simple example where the first argument is not 0. It's the successor, the mathematical successor of 0, which we usually call 1. When we add together the successor of 0 and 3, what do we get? Well, you could say 4. Okay, your mind is leaping ahead based on intuition you've built over your last 19 years or so of your lives. Okay, but a more interesting way to think about it is the sum of the successor of 0 and 3. And I want you to repeat this 10 times to yourself. I'm going to say it slowly. The sum of the successor of 0 and 3 is the successor of the sum of 0 and 3. Okay. Okay. Now, what is the sum of 0 and 3? Well, we already have a rule for that. If the first argument is 0, then the sum of 0 and anything is just 3. So this term, add 0, 3, reduces to just 3. And so the result is the successor of 3. So 1 more than 0 plus 3 is 1 more than 0 plus 3. Say it to yourself 5 times. I'm going to stop right here. The sum of the successor of 0 and 3 is the successor of the sum of 0 and 3. So you can see what I've done here. I've simplified the problem of adding 1 and 3 down to the problem of adding 0 and 3, and then taking the successor of the result. In other words, I've stripped one successor off of the first argument to the addition operation. I compute the sum of that one smaller number with the second number, and then I take the successor of that. And what's going to happen when I do that over and over and over again? No matter how large the first argument n is, it's successor of successor of successor of successor of successor dot 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 of 0. If I add that to some other number m, what I do is I say, well, take one of the successors off the front of the first number. I get a smaller addition problem. I add that one smaller number to m, and then I take the successor of the result. Well, how do I add that one smaller number to m. Well, I take one successor off that, add the smaller two numbers, and then put the successor in the front of the result. So suppose then, in general, let's look at the fourth line in this chart. I'm adding the successor of n and 3. Oh, I've got this wrong. No, I don't. Good. I don't have it wrong. I got scared for a minute. Suppose I'm adding one more than n, and that's another way to say the successor of 3. I'm adding one more than n and 3. How do I do that? Well, the result is one more than the sum of n and 3. In other words, if I'm adding 1 plus n and 3, the result is 1 plus n plus 3. And adding n and 3 is easier than adding n plus 1 and 3. The way I add n and 3 is I see first is n 0, and if it is, I just return 3. Otherwise, I compute the sum of n minus 1 and 3 and add 1 to that. And so each time through this sort of loop, I'm peeling 1 off of the first argument, computing the sum of the remaining two values, and then taking the successor of that. Okay, and that leads to the second key rule for doing addition. If I'm adding the successor of n, look at the last row in the chart, and any m, the answer is, well, it's one more than the sum of n and m. And adding n and m is easier than adding n plus 1 and m. I add n and m, get a result, and then just take the successor of that, and that's going to give me the right answer. Okay? That's how mathematical addition is actually defined. Okay? We're not talking about symbolic representations here per se. We're just talking about how numbers are defined, how natural numbers are defined, and how addition is defined as a function, as a binary operation, as an operation that takes two natural number arguments and returns a natural number result. This is the mathematical definition of addition. So I'm going to highlight the two general purpose rules here. The first rule says if you're adding 0 to any natural number m, the answer is just m. The second rule is if you're adding one more than some other number to m, then what you do is you compute the sum of n and m and take one more than that. And computing the sum of n and m is easier than computing the sum of n plus 1 and m. And because n has to be finite, and the successor of n has to be finite, and every time we apply this definition, we take 1 away from n and put a successor in front of the result, eventually we're going to be adding 0 and m. And by the first rule, that will return just m. And that is how addition is defined mathematically, by these two cases. And the two cases correspond to the two ways in which we can construct a natural number. A natural number is either 0, or it's one more than some other smaller natural number. Those are what we call the two constructors, if you will, for building up natural numbers. And when we want to define operations involving natural numbers, one natural way to do it is by case analysis, where we ask, oh, we're given some natural number n. Which case is it in? Is it 0 or is it not 0? Is it 0 or is it the successor of some smaller number, which makes it definitely not 0? Those are the two cases. So what we've done here is we've given two rules, the second one of which is recursive, because we're applying the addition operator to compute the result of adding successor of n and m. We're applying that very same operation to a smaller problem of the same kind. So we have these two rules, one base case, as we call it, one recursive case. The cases correspond to the two possible ways in which we could build the first argument. Okay? So we would say that we're defining this function by case analysis on the first argument. One case, two cases, and where the second case is recursive because it uses the function that we're defining. And the reason that that isn't really circular is because invoking that function again is guaranteed to apply to a smaller problem instance where n is smaller than successor of n. And we know that we can only take n minus 1 or strip away a successor from n a finite number of times. And so what we're going to end up with is a whole long string of successors applied to m, which is a natural number, which is some more successors maybe, or 0. So we have defined addition by case analysis on the first argument. A natural number is either 0 or it's the successor of a one smaller natural number. The add operation takes two natural numbers and returns a third. And addition, that function is defined in exactly this way. Case analysis on the first argument. Notice that in the second argument, m, we don't do anything with it. Okay? If the first argument is 0, we just return m. If the first argument is the successor of n, well, what we're going to end up doing is applying that many successor functions to m. Okay, so if n represents 2, successor of 0, and m represents 1,000,000, we're going to end up with the successor of 1,000,000, which is 1,000,002, which is just what we want. Okay, so here we have written a mathematical specification of natural number addition. What we're specifying is what addition actually means in the domain of natural numbers. Okay, so this whole conversation for the last slide or two has been about the domain on the right-hand side of our chart of natural numbers. So just in case you haven't quite seen it yet, it's really worthwhile to work out some concrete problems. So suppose we want to confirm for ourselves that this notion of addition actually makes sense. So let's suppose we want to compute the sum of 3 and 2. Well, 3 being a natural number is really understood to be the successor of the successor of the successor of 0. And 2 being a natural number is the successor of the successor of 0. You can think of the first argument here in orange as being a representation of 3, or n, and 2 as being a representation of successor of 0 as being a representation of 2, which is our m. Okay. Now, I've put square brackets around the sum that remains to be computed. And we're just starting off here, so what remains to be computed is the successor of the successor of 0, which is 3, plus the successor of 0, which is 2, 3 plus 2. Okay. So let's do case analysis on the first argument. Is the first argument 0? No, it's the successor of something. And the something is successor of 0. In other words, the first argument is the successor of 2. So we're adding the successor of 2 and 2. And our second rule says the result is the successor of adding this part and this part. So we have the successor of the sum of 2 and 2. So we started with this to compute the sum of 3 and 2, and now we just need to compute the successor of the sum of 2 and 2. Well, let's do, and so here's the remaining sum inside the square brackets. So when we apply our rule to that sum, we get, well, is the first argument 0? No. It's the successor of something, and the something in this case is this representation of 1, okay, plus m. And our rule says if we're adding the successor of something and m, the result is the successor of the something and m. So that's what this whole thing here is. And of course, we have to take the successor of that from the first time around. So we've got the successor of the successor of 1 plus 3. So we went from computing 3 plus 2 to computing 1 more than 2 plus 2, and that's 1 more than 1 more than 1 plus 2. And we apply the same rule again, right? The first argument in the remaining sum is not 0, so we compute the successor of 0 plus m, which is 2. The remaining sum to compute now is 0 plus 2, and now the first rule applies, because the first argument is 0, and the second argument is, well, it's still m, which is 2 here, and so the remaining sum evaluates to just the second argument, which is successor of 0. And so at the end of the day, we've computed our result, successor of successor of successor of successor of successor of 0. And that represents 5, or that is 5, if you want to think about it that way. Okay, so these two rules, one a base case and one a recursive case, based on a case analysis of the first argument to the addition function, gives us a precise mathematical definition of addition. And this is going to work for adding any two numbers, no matter what they are. In fact, this is just how mathematicians define what it means to add two natural numbers. Okay, so that's on the domain side. That's on the right-hand side of our, symbolic structure interpreted as meaning domain. We're on the domain side. Now let's talk about representations. Let's talk about building a discrete structure, okay, that will allow us, or I'll just call it a discrete structure, okay, again, comprising a type, some operations, some properties, and some relations. Let's think about a representation of that concept of natural numbers based on Peano's axioms. We're going to represent natural numbers using the type nat, in which 0 and the successor of n are the two forms that a given natural number can take. Okay, and now we're going to define addition. In this slide, we look at how to define an addition function on nats. Okay, so if n is now a value of type nat, in other words, it's either the symbol 0 or it's the successor of some one smaller number, and here I'll use n prime. I used n on the previous slide. The prime has no real significance here. It's just sometimes we do this. So a natural number is either 0 or it's not 0, in which case, or a nat rather, is either 0 or it's the successor of some object that is itself of type nat, here called n prime. The second argument is any nat m, representing some natural number. And the way we're going to define this addition function on these symbols is if the first argument is 0, we're just going to return the second argument. Okay? If the first argument is not 0, then it's got to be the successor of some one smaller nat, which itself is either 0 or the successor of an even smaller nat, which itself is either 0 or the successor of an even smaller nat. And you can see that eventually you're going to reach 0 because these strings of successor marks applied in front of 0 must be finite in length. And so the definition here just matches the definition of the mathematics. If we're adding the successor of n prime and m, the result is the successor of the symbol obtained by adding n prime and m. Okay? Okay? And the result of this is what we call an implementation of natural number addition. And this implementation mirrors precisely the mathematical definition of addition. And this, in some sense, is really amazing. We have an operation defined on symbols that represent natural numbers, so that if we have a symbol n representing some natural number over there, and we have a symbol m representing some other natural number over there, and we compute a new symbol by applying this function, that new symbol is going to represent the sum of the two numbers over in that domain. Okay, and that is the sense in which we've now got ourselves an implementation or an algorithm, which you could apply on paper or pencil or in a computer for computing the sum of two natural numbers, represented by these symbolic strings of type NAT. Okay, great, good. So this implementation mirrors precisely the mathematical definition, and this gives you some sense of the power of what we call pure functional programming. Pure functional programming is much closer to the mathematics than the kind of imperative programming that you've always presumably or probably learned up until now using Java, Python, C++, C, or most any other standard so-called imperative programming language. Now, as we said before, we could have selected a different representation for natural numbers. Then, of course, we'd need a different algorithm for adding natural numbers. We'd need a different function definition for adding natural numbers. If, for example, we were representing natural numbers as binary strings, well, this doesn't work at all. We need a different function definition for adding numbers that are represented in binary, and you'd need yet a different algorithm to add natural numbers represented in decimal. And that's the algorithm that you learned back in, second or third grade, where you learned how to add, arbitrarily long natural numbers represented by numerals in decimal or base 10 notation. Okay. So here we get a very, very, very clear function definition because it corresponds directly to the mathematical definition of the natural numbers and of natural number addition. The downside is that it's not a very efficient way to actually compute sums of natural numbers. Okay, so kind of summing up a little bit, what have we done here? We've defined a data type called NAT. We interpret terms of this type, such as 0, suck 0, suck 0, suck 0, and so on and so forth. We interpret those terms as corresponding to or meaning natural numbers in the imaginary conceptual world of mathematics. And we've defined a function addition, a function add, that operates on values of type NAT. It operates on these symbols, but it implements correctly the concept of mathematical addition, which is to say that it preserves the correspondence between the arguments and their the result of applying add and the arguments to real addition and the result of applying the real addition operation. Okay, so going through the bullets here, we've represented natural number objects in the domain as symbolic terms of type NAT. We've represented natural number addition in the domain as a function of this type. And here's how we'll write the type of a function. The type of our add function is read as NAT to NAT to NAT. In other words, it's a function that takes one natural number and then another natural number, and that returns a third natural number represented as NAT. So really add takes two arguments of type NAT and returns a value of type NAT. And the value that's returned represents the sum of what the arguments represent. I know I've said it 50 times now, but you really want to wrap your head around that correspondence between the symbolic domain and the domain of that symbolic world and the real world or math world domain that it's being used to represent. And the idea now is that we can compute and reason formally about natural numbers in terms of this particular representation of natural numbers and this particular representation, if you will, of how one can add natural numbers. A representation in the form of a recursive algorithm that takes two objects of type NAT as its arguments and returns another object of type NAT as a result. Okay, so we're now at the end of this lesson, and I want to just broaden this out from the example involving NATs to sort of where we're going a little bit more broadly. Mathematicians and computer scientists have designed many discrete structures. Okay, in this class you'll learn about some of the most fundamental of discrete structures, particularly important for computer scientists to understand. You'll understand how they're defined in a completely precise way, and how these definitions can be used for both automated computation and for, in general, semi-automated, sometimes necessarily human-assisted logical reasoning. Okay, so I'm distinguishing here between automated computation and logical reasoning that might require human involvement, in particular to construct proofs of propositions, which is a phrase that indicates sort of, where we're headed over the longer period of this class. So here are some of the discrete structures that, you already know about some of them, and you've probably heard about the rest, but in this class we're going to make these ideas really, really very precise, and in particular we'll look at data types, operations, properties, and relations involving discrete structures that can be used to represent Boolean values and Boolean algebra, operations on Booleans like and or and not, natural numbers and arithmetic, which we've already talked about here. We're going to talk about tuples, which are ordered pairs, ordered triples. We talked a little bit about some examples of this earlier in this lecture. And unlike lists or sequences, whose elements must all be of the same type, at least in the world of our class here, tuples can have values of different types. So for example, whereas we can have a list of cars that can't have animals in them because it's just a list of cars, we can have a tuple whose first component is a car and whose second component is an animal and whose third component is a natural number. Okay. We're going to talk about trees of objects, and you've already been introduced to the notion of trees. And now, because you've seen the inductive definition of trees and you've also seen an inductive definition of natural numbers, I hope that you can begin to see that this notion of inductive definitions is going to carry us a very, very long way. We're going to talk about sets and relations in this class, and sets and relations go to notions of properties and relations. And finally, formal languages, in particular languages like predicate logic and propositional logic, which we're going to talk a lot about. Languages are themselves discrete structures. Programming languages are discrete, give us ways of constructing discrete objects called programs. And there's only certain ways we can put them together. So for example, a simple program is either nothing, or it's empty, or it's an assignment statement, or it's two smaller programs glued together by a semicolon. And that gives rise to infinitely long sequences of, assignments in this case. Okay, and so taking these ideas that we have introduced pretty quickly at the beginning of this semester will take you really, really, really far in being able to think about and reason about and ultimately compute in all kinds of interesting ways. And one of the kind of capstone ideas in this class is that proofs of certain kinds of logical propositions can themselves be understood both informally, but also as values of certain formal types. Proofs are values of the propositions that they prove, and we think of propositions as types. But that's getting ahead of the game here. You can stop the video and go back and play that 4 or 5 times if you want. I'm not going to get into it right here. But the walk-away message here is that these notions of inductive definitions, you've already seen they're incredibly powerful. In just a few lines of code, we can define representations of the natural numbers, of algorithms involving natural numbers like addition, of discrete structures like trees, and algorithms for, let's say, counting the number of nodes in a tree. These ideas will take you a very, very long way as computer scientists. Okay, so in this class, you have the fortune or the misfortune of being in Sullivan's version of CS 2102 this semester. And the distinguishing characteristic of this particular version of 2102 is that we take a computational approach in this class. In other words, we're going to make the ideas that we talk about precise by implementing them. And we're going to implement them in the language of what we call the lean prover, which you've implemented and maybe played around with a little bit. The language of the lean prover is itself a formal logic. It's called a higher order constructive logic. And it's so expressive and so easy to work with once you've gotten mastery of a few syntactic issues, where really the syntax is just the syntax of a logic, that you're going to be able to embed definitions of all of the things that we've been talking about within Lean. So in the next short video, we'll go through how to formalize our definitions of natural numbers and natural number addition and maybe some other operations in the Lean prover. And what I hope you'll see is that what we type into Lean is, in essence, just the mathematics, albeit with, particular syntax. And, you're in a business where you're going to have to learn the syntaxes of innumerable languages over your career. So, there's a little overhead here to taking a computational approach, but I think it will help you to master these ideas much more deeply and to see in very precise ways how the intuition that you gain by studying this stuff can be turned into something really powerful. Okay, powerful in the sense that you can not only think better about the material of discrete mathematics, but you can actually automate logical reasoning and all kinds of computation. Okay, so here are some of the concepts that you'll have to learn that are not about, here are some of the concepts that you'll have to learn to be able to apply these ideas using the language of the Lean prover. At the high level, these are concepts in what we call pure functional programming as opposed to imperative programming, as in C or Java or C++ or Python. And you'll learn some basic concepts in what we call type theory. Okay, in terms of pure functional programming, you've actually already seen a lot of what you need to know. It includes inductive data type definitions, including the notion of constructors, that are the ways in which you can build values of a given type. It includes defining functions by case analysis, where we look at an argument and take it apart into its pieces and see how it was built. Is it either zero or is it the successor of one smaller number? For example, we've taken apart a natural number that's not zero into a successor and some one smaller number, and then we recursively apply a function to that one smaller number. Okay, that's taking a value apart into its pieces we call destructuring or deconstructing. So we can construct values of inductively defined types, and we can destructure or take apart values of inductively defined types, and then define how our functions behave based on what we find when we do that kind of case analysis. You're going to need to learn how to define functions by recursion, which you've already seen about, and to really understand why recursions, even though they seem to be circular definitions, they're well-founded, which is to say that circularity doesn't keep going forever. It always terminates after a finite number of steps, which means that these recursions always produce an answer. They don't ever go into infinite loops, so they always produce answers. Okay, so our function definitions will be what we call total function definitions, at least for a while, where given any two arguments, you're always guaranteed, at least in concept, if your memory, the machine you're using has enough memory, you're guaranteed to get a result. Mathematically, the results of these functions are always well-defined. Whereas a program that goes into an infinite loop, right, it implements a partial function in the sense that for some arguments you don't get any answer at all. Okay, functions for a while in our class are going to be total functions only. And finally, you're going to need to understand the notion of strong static type checking. And this is a particularly critical feature of Lean, which is that it won't let you get away with type errors. If you try to pass an argument of one type to a function that expects an argument of a different type, it doesn't work. Okay, and in particular, when we think of propositions as types and proofs as values of those types, if you claim that a proof is a proof of some proposition, but it's not actually a value of that type, it's not going to type check. You're going to get an error, and you're going to know that your proof is wrong. On the other side, once you construct a value that type checks as a proof of some proposition, you can be almost absolutely sure that you've got a valid mathematical proof. Okay, and so you're working with what we call a proof checker. And it's really cool to have a proof checker who's not a human being and who can give you instant feedback on whether or not you've constructed a correct proof of a proposition. Okay? Again, there's some overhead, there's some extra learning, but at the end of the day, if you really master these ideas, it's extremely powerful and it will make you a very, very, very good computer scientist. So I really urge you to try to get beyond the notion that you're learning a bunch of irrelevant new syntax in this class. The language that you're going to learn is a formal logic. It is an extension of, if you will, ordinary predicate logic. And learning it will give you a foundation in logical and automated reasoning that will last you the rest of your careers in computer science. Okay, so, brace yourself a little bit, but don't be scared. I'm going to help you through this. It's not going to be terrible. In fact, it's awesome. When you get a proof to type check, it's going to be like, yes, I got it. Okay, it's like a game. Ultimately, it's like playing puzzles, finding ways to prove propositions by building values that actually check out as being values of a particular propositional type, proofs of a given mathematical or logical proposition. Okay, so in terms of basic type theory, you're going to need to learn about this notion of static and strong type checking, computational versus logical types. I don't expect you to know what that means right now. Propositions as types, whose values are proofs. I don't expect you to have anything other than a glimmer of intuition for what that might mean. And how we can represent properties and relations as parameterized families of logical types. That sounds terrible or scary or just cool. And again, I don't expect you to know what that means right now. But by the end of the class, I think you will. And I hope you have fun with it. Okay, so in wrap up, we represent and design representations of objects in real and imaginary worlds and the operations to which they're subject. This allows us to reason about a domain by manipulating symbols that represent things in that domain. So for example, we can evaluate a sum of two natural numbers by evaluating the results of adding two representations of those natural numbers. And we did that in this class. Okay, we can represent physical, mathematical, imaginary worlds in this way. And this is generally basically what we do as programmers. We use discrete representations of things in some domain that we're interested in working in order to reason about and compute about that domain. And in some cases to control that domain by issuing signals to robot arms and accelerators and rocket engines and sensors and so on and so forth. Okay. Good.